Welcome to Lesson 4.3, Rates of Change and Other Applications. This section covers Topic 4.3 from the 2019 course and exam description, Rates of Change in Applied Contexts Other than Motion. The standard for this unit is CHA3.C.1. The derivative can be used to solve problems involving rates of change in applied contexts. Our instructional objective is that students will be able to interpret rates of change in order to solve problems in applied contexts. Our inquiry question is, how can derivatives allow us to solve real-world problems involving rates of change? In this lesson, we will shift our focus from physics and vertical motion problems into the world of economics, business calculus, and other rates of change. When business owners calculate profits for their company, many different factors must be considered. For this course, we want to explore marginal analysis as it relates to quantities such as fixed costs, revenue, and profits. You have seen similar exercises with linear cost function, but we want to explore scenarios of a nonlinear nature. Let's begin by defining some new vocabulary terms. The cost function, C of x, is the total cost of producing x units. The average cost is the cost function divided by the number of units, including the fixed operating costs. The revenue function, R of x, is the total revenue received for the sale of x units, and the profit function is equal to the revenue minus the cost, R of x minus C of x. We use the Greek letter pi to represent our profit function. In marginal analysis, we have a method of estimating how revenue, costs, and profits change when the input increases by one additional item. The graph of a nonlinear function is not curving too rapidly near the point of tangency, then the slope of the tangent line can be used to give us a close approximation for how the quantities change in a relatively small neighborhood. The marginal cost, MC, is equal to C prime of x, is the rate of change, the derivative, of the cost function. It approximates the cost to produce one more item, that is, the additional cost at the margin. To find an exact amount to produce one more item, use the original cost function, C of x plus 1 minus C of x. Let's look at example 1. The cost to translate documents into another language is a function of the number of pages. The cost function is given by C of p equals 0.002 p to the third minus 0.1 p squared plus 8.75 p. Calculate the marginal cost for translating 10 pages. First, let's find the derivative of our cost function. C prime of p is equal to, and taking the derivative using the power rule, we have 0.006 p squared minus 0.2 p plus 8.75. Now, to calculate the marginal cost for translating 10 pages, we need to find C prime of 10. And this is going to be equal to $7.35 per page. And we get that by substituting 10 for p into our derivative. The next question asks how this compares to the exact cost to translate 10 pages. So to find this, we'll actually find C of 11 minus C of 10. And substituting 11 into the original formula, we have 86.81 minus 79.5. And so the exact amount is $7.31 per page. And so our marginal cost is a reasonable estimate. In example 2, we want to look at a graphical representation of marginal cost. So marginal cost is the cost of producing one additional item using the slope of the tangent line at the previous value. So here we have a cost function C of x. And you can see that we have a y-intercept for our cost function. This corresponds to the cost of producing 0 products. And so we call these fixed costs. And they include things like utilities, electricity, if you're paying a lease on your production facility, etc. And so then there's the actual cost of producing one additional item. Now, as you can see, the production cost is actually increasing as a function of number of items produced, and that means that the slope of the curve is increasing. To find the actual cost of producing one additional item, let's look at the cost of producing 100 items. And so this corresponds to C of 100. That's the cost of producing 100 items. If we produce one additional item, we can find the actual cost by looking at the average rate of change. And so here is 101 items, and the corresponding cost would be C of 101. And if we graph a secant line through those 2 points, we can calculate the average rate of change. C of 101 minus C of 100 divided by 101 minus 100. And that gives us the actual cost of producing one more item. And it's just the difference between C of 101 and C of 100. So this distance is our actual cost. One of the things that we can do, though, is use the instantaneous rate of change at 100 items, and in this case we have a tangent line at x equals 100. We can use that tangent line as an approximation of how much it will cost to produce one additional item. And so if we look at the intersection of our tangent line with our vertical line at x equals 100, we can see that that corresponds to a different y value. And it is the distance between C of 100 and this intermediate value here that is the marginal cost. So this is an estimate for the additional cost of producing one unit. And you can see that there is some small error or deviation between the actual cost and the marginal cost, but it's pretty close. And so what we're doing is we're using something called local linearity. So within a close neighborhood, the function can be approximated using the tangent line. Well, what's a close neighborhood? Well, the difference between 100 and 101. So basically, an increase in x values of 1 unit is pretty close. That's close enough that we can use local linearity. And so in business, they use marginal cost because linear functions are easier to work with than quadratic or exponential. So this gives us kind of a nice picture of how all of these things fit together. And so the marginal cost is an approximation for the actual cost. Now let's look at example 3. The cost of producing a set of Bluetooth headphones is given by the production manager as C of x equals 1500 plus 50x plus 0.01 x squared. In part A, they want us to find the marginal cost function and then use this function to estimate how fast the cost is going up if the company produces 100 sets of headphones. So the marginal cost is going to be the derivative of the cost function. So the derivative of 1500 is 0. The derivative of 50x is 50 plus, using the power rule, 2 times 0.01, we get 0.02 x to the first power. And so we have our linear function. Now they want us to find an estimate for how fast cost is going up if the company produces 100 sets of headphones. In other words, they want to know what the slope is at x equals 100 for this function. And so we'll find C prime of 100. And so this will give us $52 per set of headphones. Part B says compare your result from Part A to the exact cost of producing the 101st set of Bluetooth headphones. Well, remember, they're looking for the average rate of change here. So let's find C of 100. And so the cost of producing 100 of these is going to be $6,600 if we just substitute 100 into our cost function. And the cost of producing 101 is then going to be $6,652.01. And so the actual cost is going to be C101 minus C100. 100. And so subtracting these, we get $52.01. So close to our marginal cost. Now in part C, they want us to find the average cost function, C bar of x, and then evaluate C bar of 100, giving an explanation in the context of this problem. Well, C bar of x is equal to the cost function C of x divided by x. So that's going to be 1500 plus 50x plus 0.01 x squared over x. And so this becomes 1500 over x plus 50, the x's cancel, plus 0.01 x. One of the x's cancels. So that means that C bar of 100 is going to be 1500 divided by 100 plus 50 plus 0.01 times 100. And we have 15 plus 50 plus 1, and that's equal to $66. And so this means that when 100 headphones are produced, the average cost is $66 per set. In example 4, we're told to suppose that the new Bluetooth headphones from example 3 are sold for $125 each, and they've asked us to write the revenue function. Okay, so the revenue function R of x is going to be equal to 125, that's the value in dollars per item, times x, which is the number of items. Now in part B, they want us to write the profit function. So remember, the profit function is going to be pi of x, and that's going to be revenue minus cost. And so that'll be our revenue function from part A, 125x minus the cost function from example 3. So that was 1500 plus 50x plus 0.01 x squared. And let's go ahead and simplify that. And we have negative 1500 plus 75x minus 0.01 x squared. In part C, they want us to find the marginal revenue function. Well, marginal revenue is going to be R prime of x. And if we take the derivative of r with respect to x, we get a constant value, 125. In part D, they've asked us to compute the marginal profit function if 100 sets of headphones are produced and sold, and then interpret our findings. Well, marginal profit is going to be P prime of x. So if we go back and we take the derivative of this function here, we get 75 minus 0.02 x, and that's going to be our marginal profit. Now they've asked us to find the marginal profit for 100 sets of headphones, and so we just simply substitute in 100, and that's going to give us $73. Now we have to interpret this, so this means that when 100 sets of headphones produced and sold, profit is increasing at a rate of $73 per set. Now in part E, they ask how many headphones should the company produce in order to maximize their profits. Well, let's look back at our profit function. So here we have pi of x is equal to a quadratic that has a negative leading coefficient. Well, if you think about this, it's an upside down parabola. And so it should make sense that wherever the slope is equal to 0 is going to be the maximum value. Now, if it were quadratic with a positive coefficient, then the parabola would open up, and the place where the slope equals 0 would be a minimum. But in this case, we're wanting to maximize this function, p of x. So let's do this. Let's find out where the derivative is equal to 0. Well, the derivative of the profit function we have already found. That was marginal profit. So we can do 75 minus 0.02x equals 0. And so that means that 0.02x will be equal to 75. and x will be 75 divided by 0.02, and that's going to give us 3,750. So we can say that profit is maximized where pi prime of x is equal to 0. The company should produce 3,750 sets of headphones. If they produce fewer or more than 3,750, then they will not make the maximum amount of money that they can make. Now let's look at a graphical representation of marginal cost, revenue, and profit. So in the graph shown at the right, notice that the break-even points occur where the revenue is equal to the cost. So a company would want to know how to make the most profit possible. And so the maximum or minimum profit can occur where the marginal cost is equal to the marginal revenue. In other words, where c prime of x, our cost function's derivative or slope, is equal to r prime of x, the tangential slope of our revenue function. However, maximum or minimum profits do not necessarily have to occur where MR equals MC. They could possibly occur at endpoints. In example 5, we're told that an office supply manufacturer produces spiral notebooks for interactive student notebooks. We're told to find the quantity X that maximizes profit if the total revenue, R of X, and the total cost, C of X, are given in dollars by the functions R of X equals 8x minus 0.004x squared, and C of x equals 700 plus 1.2x. We're also given that the domain for these functions is 0 to 1,000, not inclusive. What production level gives the maximum profit? In other words, how many of these notebooks should they produce to maximize profit? Well, to find that, we're going to set marginal revenue equal to marginal cost and solve for x, the number of notebooks produced. So let's begin by finding marginal revenue. So MR is going to be equal to R prime of x. And that's going to be, using the power rule, 8 minus 0.008x. Now, marginal cost is going to be C prime of x, and that is just simply going to be 1.2. Now, setting marginal revenue equal to marginal cost gives us 8 minus 0.008x equals 1.2. And if we subtract 1.2 from both sides and add 0.008x to both sides, we get 0.008x equals 6.8. And solving for x, we have 850. Now I'm not done. And the reason is I want to check to make sure this is a maximum and not a minimum. And the way that I'll do that is by plugging in a point to the left of 850 and a point to the right of 850. So remember we said a minute ago that when we set the derivative equal to 0, that just simply means that the slope is 0 and it's a horizontal line. So it doesn't necessarily have to occur at the top of a function. It could be occurring at the bottom. So it's important to do this check. And remember also that we're told that maximum profits can occur at endpoints. So I want to be sure and see what happens at 1,000. So here's the idea. If indeed we've done this correctly, and we have a parabola that's inverted, then the slope is going to be equal to 0 at that maximum value. And so just to verify that that is indeed the case, if that occurs at 850, I want to pick a point to the left of 850 and a point to the right of 850, and I want to check to make sure that I don't have maximum values there. So for my check, I'm going to make a little t-table, and I'm going to look at X values, and I'm going to look at the corresponding marginal revenue, and we'll just do this on the calculator. So at 850, we have that marginal revenue is equal to marginal cost. Let's look at 849, and let's look at 851. So at 849, the marginal revenue is going to be $1.21, and that's actually greater than marginal cost. Marginal cost was 1.2. At 851, we have $1.19, and that's actually going to be less than marginal cost. And so it looks like our point whether equal is going to be when x is 850. But let's do one more check. Let's plug in that endpoint, 1,000. If we plug 1,000 into our marginal revenue function, what we find is that our marginal revenue is actually equal to 0, so that's not going to be it. So the next thing that we might want to think about is, what are these maximum profits going to be? Well, let's find our profit function value for 850. So pi of 850, that's going to be revenue of 850 minus the cost at 850. And so we can do this on our calculator, and we get $2,190. So now we're going to make a conclusion. Therefore, producing 850 notebooks will maximize profits at pi of 850 equals $2,190. In example 6, we see the table below shows cost and revenue for the production of a widget. Use the table to answer the following questions. In question A, it asks, what is the price of the widget? So at first, this may seem a little frustrating since there doesn't seem to be any information about price in this table. And so we have to think about what we have here instead. X is the number of widgets produced. R of X is the revenue function. C of X is the cost function. So think about the revenue function. The revenue function is equal to the number of items produced times the price per item. So to find the price, all I really have to do is take revenue and divide by the number of items produced. We can't do this for 0 items produced. We can't divide by 0, and this would be an indeterminate form. But let's look at the next point here, 200. If 200 widgets are produced, the revenue is 600. And so it stands to reason then that our price, P of X, is going to be the revenue divided by X. And so if we were to do 600 divided by 200, we would get $3 per widget. And that actually is consistent. 1200 divided by 400 is 3. 1800 divided by 600 is 3. 2400 divided by 800 is 3. 3000 divided by 1000 is 3. So $3 is going to be the price of one widget. Now, what are the fixed costs? Well, remember that the fixed costs, that's what you pay when you make no widgets at all. This is the cost of your utilities, your overhead, insurance. So from the table, that's going to be $800. And then in part C, it says at what production level X is the profit for the widget maximized? Explain your reasoning. Well, remember that profit is pi of X, and that's equal to R of X minus C of X. Revenue minus cost. If we produce 0 widgets, then revenue minus cost is going to give us negative $800. At 200, we're still losing money. But finally, at 400 widgets, we've hit our break-even point. And at this point, we're no longer losing money, and we've not yet started to make money. And so our cost, we're covering our costs, but we're not making a profit. We begin to make a profit at 600, and our profit is equal to 1800 minus 1375. And so really what we're asking here is, where is that difference, R minus C, the greatest amount? And so you can check these, but that's going to occur when we produce 1,000 widgets. Our revenue is 3,000, our costs are 1,850, and this is going to maximize our profit. So we can say that maximum profit occurs when production is 1,000 widgets. Pi of 1,000 is equal to R of 1,000 minus C of 1,000. 3,000 minus 1,850 is equal to $1,150. In example 7, we're told when a backpack production is 5,000, marginal revenue is $5 per backpack, and marginal cost is $4.65 per backpack. Would a maximum profit be expected to occur when production levels are above or below 5,000 backpacks? Explain. Well, let's start with what we know. Marginal revenue at 5,000 is $5. Marginal cost at 5,000 is $4.65. Now remember, these are derivatives. And so that means that what we have here are the slopes of the tangent lines for R prime and C prime. Since the marginal cost is less than the marginal revenue, the company will make more in extra revenue than it will spend extra costs. So they should expect maximum profits to be above 5,000 backpacks. In example number 8, we're looking at an exponential decay problem. Here Gabby is working on a project that watches the decline in great white sharks in the Atlantic Ocean. The number of sharks, T years since she began working on the project, is given by the function capital S of T is equal to 3,570 times e to the negative 0.2 t. Find the rate of change for the number of sharks in the oceans after 3 years. Well, rate of change means find the derivative. So we have S of t equals 3,570 e to the negative 0.2 t. So S prime of t is going to be, and if we multiply negative 0.2 times 3,570, we get negative 714 e to the negative 0.2 t. Now the next thing they've asked me to do is to find what the rate of change is after 3 years. So that means find S prime of 3. So that'll be negative 714 times e to the negative 0.2 times 3. And plugging that into our calculators, we'll get negative 391.8515. And so let's interpret this now. That means that shark populations are declining at a rate of about 392 sharks per year after 3 years. So we've reported our value here to at least 3 decimal places, and we've provided an interpretation. In example number 9, Omar uploaded a funny video of sugar gliders on his Instagram account. The video went viral rapidly. The number of views t days after Omar uploaded the video can be modeled by the function v of t equals 243 times e to the 0.5 t. So this is exponential growth. What is the instantaneous rate of change of the number of views 5 days after he uploaded his video? And so we'll take the same approach that we did in the last problem. We're going to begin by finding the derivative v prime of t. And so that's going to be 0.5 times 243, and that will give us 121.5 times e to the 0.5 t. And now substituting 5 for t, we have v prime of 5 is equal to 121.5 e to the 0.5 times 5. And this is approximately 1,480.173. And so this means that after 5 days, Omar's video views are increasing at a rate of 1,480 views per day. And so once again, we have our calculated value to 3 decimal places and an interpretation in the context of the problem. In example 10, we're told, use the following table of values for the number v prime of t of gallons of water in thousands per hour, h, that are flowing into a retention pond, t hours after a severe thunderstorm. So we have volume as a function of time. So A, what is the interpretation of v prime of t? Well, v prime of t is the instantaneous rate of change of the thousands of gallons of water per hour after t hours flowing into the retention pond. In part B, we're told to estimate v prime of t and explain the meaning and context to the problem. Actually, this should be v prime of 2. So v prime of 2 is approximately v of 2.5 minus v of 2 divided by 2.5 minus 2, 1.24 minus 1.15 divided by 2.5 minus 2. And this is also approximately v of 2 minus v of 1.5 over 2 minus 1.5. 1.15 minus 0.93 divided by 2 minus 1.5. So what we've done is we have calculated an average rate of change over this interval and an average rate of change over this interval. And so this gives us a means of estimating. So v prime of 2 is between 0.18 and 0.44. This means that after 2 hours, between 180 and 440 gallons of water are flowing. Finally, in part C, it says, when does the rainwater flow begin to slow down? Estimate the instantaneous rate of change at this time. Well, if we look at our table, we can see that, say, the volume of water is increasing until we get to 2.5, and then it begins to decrease again. So this would indicate perhaps a drop-off in our flow. So let's make an argument. V of 2.5 is greater than v of 3. So we expect the flow to begin slowing for some time t between 2.5 and 3 hours. And estimating that flow at 3, v prime of 3 is approximately 1.05 minus 1.24 over 3 minus 2.5, and this is approximately negative 3.8, and so this would be about negative 380 gallons hour. So we are definitely having a decrease in the rate of flow, as it's now negative.